Everyone, welcome you back. Thanks for your time. Appreciate your time on making out for this webinar. So I conduct and I think my introduction. I keep doing this technical webinar every month. I'm Geeta. I work as a director on tools at GSAS and SPL, GSAS Microsystems Private Limited. We're the only authorized and brand distributors of ARM software solutions in India. And I've been working on ARM technology and the solutions for past more than 25 years. So I have a good experience on the ARM technology and the solutions. And every month I do conduct a technical webinar on the features of the ARM processor, softwares, whatever we offer. And we shall be sharing the email as soon as the webinar date is fixed up. So thanks for your time. We appreciate your time in making up for this webinar. So let's start. So basically, today we are talking about Cortex Microcontroller Software Interface Standard, CMSIS. Many of you might have been aware what is CMSIS. If the team is working on Cortex-M-based microcontrollers or even Cortex-A-based processors. But this is a second or the extended version of the webinar which I did last month. In that I spoke about to quickly give the gap, to quickly bridge the gap between the previous month webinar and this month's webinar, so that if some of the audience could not make up for the last month webinar, so just to give them the heads up, for some who have already attended, please bear with me. It could be a repetition for you, and it could be a kind of brushing up your mind. Okay, so my last webinar was on CMSIS. So CMSIS is basically it provides an abstraction layer for Cortex and processor-based device. So CMSIS, I just show in the first slide, it is Cortex Microcontroller Software Interface Standard. And this standard was brought in joint collaboration with ARM, semiconductor vendors like NXP, ST, Microchip, Nuvoton, Nordic, Samsung, whoever manufactures the microcontrollers based on ARM processor cores, and the software tool vendors like open source compiler, Segger, IAR, as well as the ARM, KileMD. So as per these standards, each of them, like ARM has to give some set of files. Device semiconductor vendor, or when I refer silicon vendor, has to give some set of files. Okay, so this is what CMSIS was brought up, and this is an abstraction layer for Cortex-M devices. This will make the life of the user or a developer easy. How this is benefiting the embedded developer? You'll get a software interface for silicon and middleware vendors. You'll get a consistent software interface. Like if you're working on MDK, you'll be getting the family packs or drivers from the silicon vendors, which is maintained consistent across the devices, or even across the various silicon vendors and the middleware vendors. There are so many middleware vendors in the market now, embedded domain. So they also have to follow the standards. You can use across, whatever the program you have developed or a product you have developed, you can use it across the various Cortex and processor-based device. That's the advantage for developer. So learning curve reduced, cost reduced, because the time taken to bring the product to market is fast. So the cost will be reduced for sure. So CMSIS actually gives a set of files which is compliant with ANSI, C, and C++. Okay. It also conforms to MISRA 2004 standard. So what is the CMSIS structure? Though there are various versions of CMSIS now available, if you go to arm.com, you'll get to know what are the various CMSIS standards, various derivatives of this. So CMSIS core is, these are the different things which I discussed in last webinar was CMSIS core, CMSIS-Driver, and CMSIS-DAP. So CMSIS core is an API for Cortex-M processor core or core peripherals. So CMSIS core, as part of CMSIS core, you will get a set of the functions which are used to access the processor core, Cortex-M processor core and its peripherals. When I meant the peripherals, it's the core peripherals, like it could be watchdog timer, it could be nested vector interrupt controller, it can be memory protection unit, it can be anything, it can be stick timer. So these are the peripherals which are present inside the processor core, Cortex-M core. I'm not talking about the peripherals which will be implemented by the silicon vendors. So core is specific to processor core only. So CMSIS-Driver, we have this, they give the standard API for the generic peripherals. This we are talking in this webinar. CMSIS-DAP is also I'm talking about in this webinar. This is the firmware specification for accessing the debug port of the device or a microcontroller. DSP library, basically for some of the Cortex-M devices like M4, M7, M33 based microcontrollers, they have something called as DSP libraries because these microcontrollers are digital signal controllers. So it has a Cortex-M core along with a DSP unit. So DSP is not the full-fledged DSP what you might have come across. It's a multi-line accumulate unit and you have single instruction support, single instruction multiple data. So the data processing happens faster. Then we have CMSIS-PAC. This is the device package is given in the form of packet description file, which I'll be discussing in this webinar. CMSIS-RTOS, this is a API, they give a set of APIs for the RTOS. So any RTOS can define these RTOS and they can become part of CMSIS-RTOS. So in that Kyle Artix RTOS, which comes as part of MTK software, became first to be the part of CMSIS-RTOS. It was compliant to CMSIS-RTOS. CMSIS-SVD is system year description file, and you can see here in the diagram, you can see this is a Cortex-M CPU. We have the stick timer, NDIC, which I told we have debug plus trace, other peripherals, core side. This is for your microcontroller. The microcontroller may have other peripherals also. So CMSIS core can access Cortex-M CPU. CMSIS core give you access to the CPU processor core. Sysdig you can configure, I told. NVIC debug trace. For peripherals, we have SVD, and for core side, we have DAP. And coming to software pack, so we have DSP, CMSIS DSP, CMSIS RTOS. RTOS, you have any RTX kernel driver for your device drivers or peripheral drivers. Okay, so this CMSIS-SVD we will be talking about in this webinar. So in the previous webinar, I covered CMSIS core, CMSIS DSP, CMSIS RTOS. In this webinar, I'll be covering CMSIS-Driver, CMSIS-PAC, CMSIS-SVD, CMSIS-DAP. So all the information about the CMSIS is available on arm.com. Silver.arm.com is now all the pages have been routed to developer.arm.com, or you can also go to actual arm.com. These are some of the CMSIS partners, some of the silicon vendors. Silicon vendors who manufactures this, who develop their microcontroller devices, and they are part of CMSIS. So once they are part of CMSIS, they have to give the supporting files for those for their devices what they are developing and bringing to market, so that the any user who selects that particular device and develop the software, it will be beneficial for them. These are some of the tool vendors. We have Kyle, we have IAR, Sega, Atomic. Atomic is now taken by ST. Resonance, RTM, Hitex, RTOS. Okay, so this was just to give a bridge or a heads up on the previous webinar. So now we will go to please put your questions on chat and mute yourself. Thank you so much. So now coming to CMSIS-SVD. So CMSIS-SVD stands for CMSIS System Year Description File. What does this CMSIS-SVD give? How this is going to help the team? Please mute yourself, or I might have to mute you. Thanks. So how this is going to help the users? So for the silicon vendors, for the semiconductor vendors, how CMSIS-SVD is able to help? It will give you early device support from tool vendors. Means once the silicon vendor develops this system your description file, that SVD file will be supported by the tool vendors like Kyle or IAR or Segger or whatever. Okay. And it will also help the silicon vendor to generate the CMSIS compliant device header. So what is this device header? Because suppose you're selecting a device. For example, I'm selecting STM32F103, which is Cortex-M3 based. So I have to program this device. I have to develop a software for this microcontroller, which is on my board. So I have to program and configure the peripherals of this controller. To access the peripherals, you need the registers associated with those peripherals. So those registers can be accessed from this device-specific header file. So in Kite project, when you create a project and select a device, you have to include the device-specific header file so that we can start developing the software for that particular microcontroller. So that's device-specific header file is also given by silicon vendor. And once this is silicon vendor designs the system, your description file, it will automatically generate the device-specific header file as well. How it is benefiting to the tool vendors? So we have a unified file format. So this SVD is being, this standard is followed by across the semiconductor vendors. So we can have the view for the early access. Even the device is released to the market by the semiconductor vendor, you can get early access to this by taking the permission from the silicon vendor. So it's the CMSIS-SVD web infrastructure. So basically, here when I told CMSIS-SVD, CMSIS-SVD is through which the device is added to the device database. For the team who has already worked on MTK, you can relate what is device database, because whenever you create a new project in Kyle, and the first box window that opens is the device database window, where we have to select what is the device you're using for your project, for your product development. So how the device name will come to the device database? What is the process? What is the procedure? That is in this slide is explained. Okay. So this shows how the steps involved for uploading, validating, reviewing, publishing, and downloading the CMSIS-SVD file. Suppose, because I told system description file has to be developed by the silicon vendor, so silicon vendor will develop the SVD, and it will there are checks done at the silicon vendor end, and if it is passed, then it goes to SVD storage. If it is not, then that particular SVD file will be discarded. Okay. So advantage for this is, for every device, whatever the silicon vendor supports. For example, if I take LPC 1768, we have LPC 1769, we have LPC 1588, we have LPC 1589. So these are all Cortex-M3 based microcontrollers from NXP, but they're all various devices with a different set of peripherals. For each of the device, the silicon vendor can create an SVD file and start storing that in the SVD storage. If any user wants to get access to this, they can take a access permission from the silicon vendor, and they can get the access to that specific SVD file. Okay, so once the SVD files comes to the SVD storage. So SVD storage is nothing but the set of SVD files for the various devices, microcontroller devices, M3 base, M4 base, M7 base, whatever it is. All those devices are dumped in this, stored in this SVD storage. So in this SVD storage, when they create an SVD file, the SVD file will also have the time, date, the date when this particular device will be published. So published means adding it to the device database. So once the date reaches, those files, those devices are added to the device database. So it is published. From the device database, you can use it. It is available for the public download by accepting the EULA. That is, when you install the Kyle MTK software, you have to accept the terms and conditions. Then you'll be able to use these devices in your software. So this is how CMSIS, this SVD file will help the silicon vendors to add the devices as well as to publish and add it to the device data. For the device database. So any questions or any specific slides, so please put it in the chat window. I'll come to that at the end of the session. Now coming to what is this SVD file? As I told in the previous slide, for each of the device, what the microcontroller, what the silicon vendor or semiconductor vendor is developing, they create an SVD file and keep adding it in the or storing it in the SVD storage. So what is this specific file? So here, the SVD files is actually defined in the form of XML hierarchy. The device level is basically a top level of the system description file. So we have peripherals. So peripheral is nothing but the set of registers. So we know theoretically how ADC performs, how timer performs, how UART performs. But through software, how we will make the processor perform is through configuring the registers associated with the peripheral. So peripheral is nothing but the set of registers. So each peripheral has a unique set of registers. Then in the register level, we have different set of registers which are unique. So each register is it is a new register and it can be programmed to program a peripheral resource. So each register now we can register. In the each register we have fields. So each register in ARM is 32-bit. Not all the bits are used. Some bits are being reserved for future use. The silicon vendor will decide on that. So each bit has a unique definition. Not all. So one bit of 32 bits of one register will not be same as 32 bits of other register. So each register will have a unique fields, unique values. So enumerated value is what are the values for those fields, 0, 1, or whatever it is. Okay, and you have vendor extensions. This names for any custom device specification, anything on the customized extension vendor can implement. This is how the SVD file is depicted in XML hierarchy. So this is an CMSIS snippet. How when you open any SVD file, this is how you can see. For example, here they have considered timer 0. So timer 0 is a peripheral. This is the name of the peripheral. This is the base address. So what is the base address? This is the this is the starting address from where the registers are allocated for programming this timer 0 peripheral. So registers size, I mean how many registers you want, all this, and any interrupt, because timer is an peripheral which can generate an interrupt. So all those things can be here covered in the SVD file. So in the first slide I told SVD file is validated, it is checked. So how do we do that? ARM provides the SVD utility, which is called svd-conv.exe. This is where we checks the description file, CMSIS-SVD descriptions, and it also automatically helps the silicon vendor to generate the device specific header file. So like this, suppose you have developed your own SVD. So when you run this, if there is any validation checks, you will get an error. Otherwise, you can generate even a header file as well. So any questions, please put in chat window. CMSIS pack. So CMSIS pack is something before that I would like to show. So this is the pack installer which comes with Microvision 5 ID. So in Microvision 5, the required device support, whatever the device you're using, the device support has to be downloaded from the DFP. So these are all the packs. Okay. So you can see whatever device you're using, just type in here. And the device specific thing, it comes here. What is the device family pack we have to install? We've come to come in this particular slide, what is device family pack and all. But one thing I want to remember, I want you to know is anything in the generic where you see ARM. So all these packs are provided by ARM directly. So whichever the ARM pack required for your application, you can download it. When you install the software, ARM CMSIS, CMSIS compiler, DSP, and RTX get installed automatically. So you can see they are all up to date. Any other thing, neural networks, this is for your machine learning, artificial intelligence. This you want, you can download it. So like that, whatever pack you require, you can install it. Anything device specific, you will have that apps headers. So generic, all these are ARM is given by ARM and this is given by Silicon vendor. Right. So now we come to this. So CMSIS pack is the way of delivering. It's a mechanism how you deliver the software components, device parameters, and the board support. Many of the devices what Silicon vendors develops, they do have the evaluation boards to help the users to kickstart their application first to get hands on, get acquainted with that a particular device, and then they can develop their own hardware or POC or whatever. So first I show device family pack. As I told, in my pack installer, I had selected HTML32H7 and some particular device, whatever. So for that, it will show on the right side the pack. What is this device family pack? This device family pack has to be given by semiconductor vendor only. This has CMSIS files, that is, it has startup file, drivers, peripheral drivers, and it has flash programming algorithm. The device what you have selected has the on-chip flash, the flash programming algorithm for it, a device specific header file, system initialization file. All these are part of this device family pack. To help you get started with the device, whatever you require is given as part of DFP, and this has to be given by semiconductor vendor. Now coming to CMSIS software pack. This contains all CMSIS, generic CMSIS component. I showed in the pack installer, generic ARM drivers or ARM packs. Those are the one which comes in batteries. So you have core, DSP library, RTOS, which are all supplied by ARM. Middleware. So middleware pack contains the components which belong to the middleware. So these packs are given in the form of source code or in the form of library. In case of MDK, the middleware components are given in the form of library. Then we have BSP. BSP, as the name itself suggests, it's a board support package. So this, for whatever board you are you bought from the market, you can also check whether the silicon vendor has given BSP for that. So this has documentation of the board, schematics, it has the drivers, example projects on how to get started with the board. And then something comes as in-house software packs. This is usually developed by the user, which can be distributed within the company so that you can use that for your projects. So this is CMSIS pack description. So CMSIS packs, whatever the software packs we saw in the previous slide, they are delivered to the user in the form of packet description file. But it's an XML-based format. So what it has source code, it has header files, it has libraries, documentation, source code templates, example projects, parameters, startup program, startup code, programming algorithm, flash programming algorithm, system initialization file. All those are part of the same system. So this is delivered to the user in the form of packet PDSC, packet description file, and this can be downloaded from even the ARM site or even from the Silicon vendor site with a .pack extension. It is developed in the form of a software pack with a .pack extension, the zip format. If you double click, it will unzip the contents to the kite folder wherever you have installed the software. So this is designed for this is PDSC, can be used in any environment which is CMSIS compliant. Okay, it can be used in any environment, and it has all the files which are relevant for the user for developing the code for that specific device. The next coming to drivers, CMSIS driver. So CMSIS driver, as I told, this gives a set of APIs for accessing the standard peripherals. So what all device drivers are being given? We have for Ethernet, we have I2C, we have NCI memory card interface, NAND flash, NOR flash, SPI, UART, and USB. Suppose if I take a typical microcontroller here, you have USB controller, you have USART, you have Ethernet file layer, MAC layer, SPI, STIO. STIO is for your MCI, that is memory card interface, memory controller, and USB controller. Suppose USB controller can go to USB device driver, and that in turn can be configured through middleware pack, which has a USB stack. USART goes to USART driver. You can USART driver is given in the CMSIS driver that can be used to program the USART. Similarly, Ethernet file can be used to program the file, and this can also be a program to TCP/IP stack, which is given as part of middleware. For SPI, we have SPI driver. For memory controller, we have NAND flash, like that. Okay. For some of the silicon vendors, they do have multiple, like two I2C interfaces, two SPI interfaces, like that. So, like based on that, you have to use it. They give the standard, um, they give the generic API for standard peripherals that you may have to modify as per the device what you're using. This is how the template looks like. So this actually gives the registers, the same as the drivers. Drivers means for programming a specific peripheral. Like suppose for USART, what all you require. For timer, what all the registers, what all the functions, expected functions required. That is given in the form of a structure here. So here you can see these are all generic functions like getting the version of the CMSIS driver, initializing that specific peripheral, clearing it, allocating the memory or whatever. Then power control to initialize the power profile, that is at reset, whether you have to get the power, you are enabling the peripheral or not. Then these are all data transfer information functions like sending the data through the peripheral, receiving it, everything. And this is all device specific, like get data count. This can be for, you can associate this with a timer peripheral, like that. Okay, so control register gets status. So this is how the CMSIS driver functions are given. So here you can see this is an example for USART. Okay, for UART, what all you require first? What is the mode the UART operates? What is the data bits? Parity is there, stop bits, flow control. So these are all the functions which is required. Say driver for USART, whether here driver USART control in this function will be enabling whether it is asynchronous or synchronous and what is the baud rate set. Like these functions are, these are all the APIs which you can use in your C program directly to configure the USART of the device. So next, coming to CMSIS-DAP. So CMSIS-DAP is something all the microcontrollers based on ARM processor core. If it is on Cortex-M, it will have a debug port. It have a debug unit. We call it as ICE, and circuit emulator or a debug interface. So you can access the debug interface of that device or a microcontroller through the USB port. So the board on which the device is there, if you have a USB, micro USB or normal USB, you can connect that board to a software which is running on the host PC, and you can control the board through that software. Okay, so here you can see. So this CMSIS-DAP is nothing but a firmware. So this has for a hardware to connect to the software which is running on the host PC through a USB port. So there is an interface here. This interface will configure the USB of the particular microcontroller as a human interface device, so that no drivers are required on the host system, and we can directly control the target device on this board. So you need to have CMSIS-DAP. This is the interface. This is usually programmed in the Cortex-M microcontroller. Please note this Cortex-M microcontroller is different than the actual device on your hardware board. So through this CMSIS-DAP or debug unit, you can get connected to any of the debug unit of the particular device through either JTAG or SW. So on the host, you can have the software either MDK debugger, MDK software, or DSY debugger. When I mean MDK debugger, it's the software. It's a GUI, a software debugger where you want to see or you want to program the flash, you want to do the debugging of the code which is running on the hardware. That is software debugging. So there are many benefits of using SIM system. What are those benefits? So this provides a standardized interface for debuggers, interfaces to this interfaces to Kyle, MDK, and ARM DSY is already available. DSY is now obsolete and is replaced with the Development Studio. Kyle, MDK, and Development Studio are two different software solutions offered by ARM, which supports the various processors. Like MDK supports specifically the ARM-based microcontrollers, whereas DS supports higher-end Cortex-A 32-bit, 64-bit processor cores. So you can access the core site registers through this CMSIS-DAP on any of these profiles. Please note they have written ARM, Cortex-A, Cortex-R, and Cortex-M. This is not only limited to M, it is also for Cortex-A. So you can connect to the actual target device through JTAG 5-pin or 2-pin serial wire debugger mode. It supports multi-core debugging. So the debug units means the CMSIS-DAP interface can be easily implemented, can be programmed to any Cortex-M microcontroller. So this debug unit or this CMSIS-DAP firmware has to be there on the hardware board. So as I told, it detects as a human interface device, HID, USB cast, because you're accessing the board from the USB. So the board has to be detected. So USB detects as a HID, human interface device, where no drivers has to be installed. And using CMSIS-DAP, you can also access the MTB. So what is MTB? MTB is micro trace buffer. So in case of M3, M4, M7, M23, M33, M35P, M85, M55, all this Cortex-M processor has the higher end trace features. We call it as on-chip trace, which is data trace. Another is optional of off-chip trace, which is ETM. Means the trace is available on the processor, but why it is called off-chip traces? It is not all the devices has the ETM block. So silicon vendor, semiconductor vendor, at the time of developing the microcontroller, they'll decide whether the ETM block has to be included or not. Whereas M0 Plus was the processor core which ARM came specifically to help the users migrate their design or development from 8-bit controllers like 8051 or any 8-bit devices and move their works to Cortex-M. So they maintained the price also similarly. So not much features were implemented in M0 Plus, but it is a 32-bit processor for Cortex-M only. So some limited trace was also implemented on M0 Plus, which was MTB, macro trace buffer, where on-chip RAM of the microcontroller will be used to store the limited trace. So this appendix is just to show the how the PDSC file looks like. Files for ARM compiler GCC, because this is a standard file which is used across all the software. So you have for all the compilers, ARM compiler, GCC, all. This is simply for your CMSIS for DSP. What are all the APIs which are given as part of CMSIS DSP library? Okay. So that brings me to the end of the session. If I'll come to the chat if anyone has any questions. Yes, Tapan, we have recorded this session, and once we upload this session on the YouTube, we shall be sharing the we shall be sharing it on the on our site, GSAS. So once the link is available, we will upload it on our GSAS site and we will share it with you as well, or whoever has registered for this webinar. So does the team has any questions? I will leave my contact details here, my email ID. If anyone is interested to purchase the software, or if anyone has any technical clarifications required, you can write it to me. And if the team is looking for any specific topic that you want me to do, I can certainly do that. So my mail ID geeta@gsmspl.com and phone 93437568. So if there is no questions, I shall wind up the session. Thank you. Thank you so much for your time once again. And I shall see you soon next month in the next technical webinar. Thank you.
Thank you.